Students, in this class I will discuss the second part of aromatic electrophilic substitution reaction. First part of aromatic electrophilic substitution reaction, I have discussed the mechanism, how electrophilic substitution reaction takes place in an organic compound. Now, because this was not complete, so in the rest part I will discuss today. In last class I have done halogenation and nitration, a bit of alkylation. Now we'll go in detail about alkylation and acylation reaction. Alkylation and acylation reaction are known as Friedel-Crafts reaction. For Friedel-Crafts reaction, what we do? Benzene was treated with alkyl or acyl halide. Alkyl halide is written as RX. R stands for alkyl halide, X stands for halogen, or it is called alkyl halide. Or you can do this way, RC double bond O Cl. Cl. This group is called acyl group. Now what happened? Benzene when treated with alkyl halide, because I need an electrophile, as a result with alkyl halide I used Lewis acid as a catalyst. Suppose I have taken this alkyl halide CH3 CH2Cl and AlCl3 was used with it. AlCl3 acts as a Lewis acid. Chlorine has unshared pair of electron. Al accepts the electron and induces positive charge on the carbon atom to which chlorine is attached, and that carbon attacks the benzene. As a result, as an intermediate, this is formed HCH2CH3 plus AlCl4 minus. We consider there are many carbon atoms in an alkyl halide, but the carbon directly attached to the chlorine one that attached to the benzene nucleus. It is CH2 part attached to the benzene nucleus, then CH3. It is a pentadienyl cation. It is no longer aromatic, but benzene does not want to lose its aromaticity, because aromatic compounds are stable, hence gives its bonding electron to the benzene. And in this case what happened? We obtain CH2CH3 plus HCl plus AlCl3. In this case, one hydrogen replaced by ethyl group. Now, there are some important things takes place in alkylation reaction. Just I am discussing that. Suppose I have taken a large alkyl halide, CH3, CH3, CH2Cl. With AlCl3 was used. This carbon asterisk one to which chlorine is attached. AlCl3 accepts the pair of electron, forming CH3CH, CH3, CH2. This will be Cl and AlCl3. This induces positive charge on it, and the chlorine will be the negative part. Now what happened in this case? Because in this case if it breaks this way, in this case this CH2 part will carry positive charge like that. This carbon carry positive charge. It is 1 degree carbocation, unstable. There is rearrangement takes place. The methyl group shifts from here to here to form CH3 CH plus CH2 CH3. It is 3 degree, more stable. It attacks the benzene nucleus and replaces one hydrogen. So in this case the product will be CH, because this carbon carry positive charge that attack the benzene, then CH3 CH2 CH3. Okay, in this case it is the case benzene with an instead of this group, instead of attacking by CH2 group which is 1 degree, CH group attack it from 3 degree. This is the major product. Why rearrangement takes place? Rearrangement takes place as 3 degree carbocation is more stable than 1 degree carbocation, hence rearrangement takes place. As 3 degree carbocation more stable, than 1 degree, hence rearrangement takes place. Hence rearrangement takes place. Acha, again I am writing it. Next page I am writing it in detail about it. Suppose it was benzene. It was treated with this. With LClC as Lewis acid. This chlorine attacks by aluminium, induces positive charge on it. So we are getting two products. One of them is this. And after rearrangement, it forms this also. Okay, in this way I can so this is the minor one, this is the major one. Achha, one disadvantage of alkylation reaction is that, as I will come in detail about it later on, alkyl group is an activating group. So after an introduction of alkyl group, next alkyl group also come to the benzene nucleus. So polyalkylation takes place. It is impossible to stop the reaction after one alkyl group is introduced into the benzene nucleus. This is the disadvantage. And one more disadvantage is that in some cases there is a possibility of rearrangement also. Now, if we think of acyl halide case, suppose benzene treated with suppose CH3, C double bonded or Cl, AlCl3. Now, in this case, electron density on the chlorine atom will be less compared to this. If you ask me the question why, because CO group is electron attracting, so pushes electron. As a result, positive charge on the carbon atom of the carbonyl group is less. Hence, this substitution takes place less readily compared to alkyl halide. As the carbonyl group is as the chlorine is electron attracting, and carbonyl group oxygen joined to carbon by double bond is electron attracting, so electron density is less in acyl group compared to alkyl group. Hence, acylation reaction is less likely compared to alkylation reaction. In this case, still there is a chance of forming this carry positive charge, and this attack the benzene to form this. It's known as acetophenone. Acetophenone. But in this case, look at here, C double bond auto. Now again AlCl3 is there. This lone pair of electron attacked by aluminium. So in this case, electron density decreases on this group. As a result, further acylation reaction is less likely. So in this case, only mono substitution takes place. Why the chance of poly substitution is less? Again, I am repeating the word. Oxygen having unshaped pair of electron, AlCl3 acts as a Lewis acid. Lone pair of electron is attracted by aluminium, so electron density on the molecule decreases. As it is decreases, so less readily electrophilic substitution reaction takes place. So one advantage of acylation reaction is that only mono substitution reaction takes place. Write it properly because it is very, very important. With alkylation, polyalkylation takes place, but acylation, as alkyl group is an highly activating group, but in this case it is a deactivating group because CO group is electron attracting. Hence, further substitution hardly takes place into the benzene nucleus. Now, this is about alkylation and acylation. So, in alkylation, there is a chance of rearrangement as well as polyalkylation, and acylation, no such things takes place. And acylation reaction, only mono substitution reaction takes place. Now, I will discuss a very important substitution reaction that is called sulfonation reaction. Sulfonation reaction In sulfonation reaction, one hydrogen of the benzene nucleus replaces by hydrogen in benzene nucleus replaces by SO3H group. It's called sulfonic acid. In this case, we used oleum in H2SO4. SO3 in this case acts as an electrophile. I will tell in detail a mechanism of the sulfonation reaction because it is a bit different compared to other substitution reaction which I have discussed so far. Suppose benzene, it was treated with fuming sulfuric acid which is known as oleum. This attacked it moves over here, so forming an intermediate like that. The intermediate is unstable, is as pentadienyl cation, but compared to earlier one, the difference in this substitution compared to other are that, look at here, I am showing in the next page. In all substitution reaction, it is a two-step process. First step is slow, second step is fast. Okay, so formation of the intermediate is the rate determining step. But for sulfonation, the two steps are as follows. That means two steps has more or less same energy. Two steps to intermediate more or less same energy. As a result, in sulfonation reaction, two things might take place. Plus, there is chance for desulfonation reaction like that. As well as, because in this case reverse reaction takes place, or H gives its bonding electron and forming this. Okay, now in this case, as it is a two steps are of equal in energy and reaction is reversible, so desulfonation takes place as well as H replaced by SO3H group also takes place. And moreover, I told you in earlier reaction, as second step is not the rate determining step, so it doesn't show primary kinetic isotopic effect. That means whether it is H or D, that doesn't matter for other substitution reaction, but in this case it matters. It shows primary kinetic isotopic effect. That means if H was replaced by D, suppose look at these two cases, benzene plus SO3, now we have deuterium. H replaced by D, in this case intermediate is forming this, plus in this case we have formed this. Now CD bond is stronger than CH bond and activation energy for the CD case, suppose it is with benzene sulfonation, and in this case it is for deuterium. For deuterium, what happened? The energy will be a bit more, as the energy for as the removal of deuterium is less likely compared to loss of hydrogen. As a result, replacement of H by SO3 group takes place more readily than replacement of D by SO3 group. Hence, deuterium shows primary kinetics kinetic, isotopic effect. Now, a revision of the part what we told so far. Sulfonation difference with other substitution reaction. Sulfonation reaction. Why the difference of sulfonation with other group? Reagent is what? SO3 as an electrophile, because positive charge induced on it, because oxygen is more electronegative than sulfur. In this case, two steps. Step number 1, 2 steps more or less equal in energy. Hence, desulfonation takes place. Number 2 shows primary kinetic isotopic effect. Means with deuterium, chance for substitution is less than that of replacement of H. This is about monosubstitution reaction of benzene. Now I should discuss another electrophilic substitution reaction, that is the case of diazonium cation. In diazonium cation, what happened? Benzene attached with N2 plus. N2 plus can be written either this way or if the positive with an unshared pair of electron here, or if it moves over here, it can be this way also. Now, for substitution reaction, the second resonating structure is more likely where the terminal nitrogen carrying positive charge. Now I will discuss the difference of this diazonium cation with other electrophiles. Suppose NO2 plus or Cl plus or SO3, which we have discussed so far. These are now more or less strong electrophile, so they can readily attack benzene nucleus. Okay, in benzene this substitution reaction takes place, but diazonium cation is poor electrophile. Write it properly, poor electrophile. Hence, if the benzene ring is not activated by some substituent which increases the electron density in the benzene nucleus, no diazonium substitution takes place. So for precondition for diazonium substitution reaction is that it should be activated by a group such as OH or NH2 to the benzene nucleus. Now look at here what happened when we pushed an OH group or NH2 group into the benzene nucleus. Look at here what happened. Suppose it is benzene with OH. Because phenyl group is electron attracting, so it pushes electron over here. So it is phenolic group is acidic. It exists in the solution as phenoxidine. The phenoxidine increases electron density in the benzene nucleus. Electron density increases more in the ortho and para position. As it is a large group, so substitution most readily takes place in para than ortho. So you have the product like that. Diazonium cation attack the benzene nucleus. It is known as coupling reaction. Now, this is up to coupling reaction with phenol because phenoxide is more resonance stabilized and increase electron density more. Hence, for diazonium cation with phenol, the reaction should be carried out in alkaline medium. Why alkaline medium? As phenol is acidic, alkaline medium it forms phenoxide ion. Phenoxide ion forms increases electron density more into the benzene nuclear, so coupling reaction takes place readily. With phenol, the reaction of diazonium cation should be carried out in alkaline medium. On the other hand, if I take NH2, if I take NH2 group like that, NH2 is also activating group. In this case, the reaction should be carried out. Reaction is coupling reaction with diazonium cation should be carried out in slightly acidic medium. Why? The slightly acidic medium converted benzene to diazonium cation, which couples with the aniline part. If you make the reaction strongly acidic, in strongly acidic aniline fully converted to NH3 plus, as a result, no coupling reaction takes place. Strong acid medium. In strong acid, NH2 converted to NH3 plus, which is deactivating, where the nitrogen carrying positive charge, deactivating. Hence no reaction takes place. As a result, what we should do? We should make the reaction slightly acidic such that it converted to diazonium cation, which react with the aniline part to gives you the coupling reaction. For aniline, it should be carried out in slightly acidic medium. Phenol, the reaction should be carried out in slightly alkaline medium. Why benzene itself does not undergo coupling reaction with diazonium cation? The logic I told you, it doesn't undergo because it is a poor electrophile. Unless the electron density increases manifold, no substitution reaction takes place. Now, suppose I have taken only N2. Or now, if the positive charge on the nitrogen atom can be increased, in such case, it can couple with substituent which is not as activating as OH or NH2. Suppose if I put an NO2 group over here, NO2 group is a deactivating group. In its presence, positive charge will be more compared to this. So para-nitrodiazonium cation, the nitrogen carry more positive charge than only diazonium cation. As a result, this may coupled with anisole, which is an activating but not as activating as OH-NH2. It may coupled with para-nitrodiazonium cation, but only diazonium cation cannot couple with anisole. Logic is what? In this case, positive charge is more. As a result, because of the increased positive charge, if the electron density is not that much, still coupling reaction takes place. So in this case, we may have this product. It is OCH3. Then we have N double bonded N, another benzene with NO2 group. because this is a bulky group, so the substitution more readily takes place in the para than ortho. It is the ortho or para substitution I can write over here also. Okay, this is about electrophilic substitution reaction in benzene nucleus. But benzene is an halide. In benzene generally undergo electrophilic substitution reaction. If I take an aryl halide, in some cases there is a chance of nucleophilic substitution reaction also. I'll discuss in a bit later on, but today's class what I have discussed mostly are the case of electrophilic substitution reaction. Now look at here. Suppose CH3Cl plus OH minus. OH carry negative charge, it is called a nucleophile, it attacks the carbon atom. Chlorine polarizes the Cl bond towards itself, so the carbon carrying positive charge, as it is 1 degree alkyl halide, so the reaction will be SN2. Ultimately what happened? CH3 replaces by OH with expulsion from Cl minus. It's called nucleophilic substitution reaction. Okay, but if I take this one, with OH minus, generally no normal condition, no reaction takes place. Why? What the problem? In this case what happened? Chlorine has an unshaped pair of electron, double bond, single bond, unshaped pair of electron. There is a part of resonance. Due to resonance, CCl bond in aryl halide has partial double bond character. That means it will be like that. This moves over here, this moves over there. Carry positive charge. The chlorine attached to the benzene become double bonded, that is more stable. Hence replacement doesn't take place as readily as alkyl halide. Okay, as a result aryl halide generally does not undergo nucleophilic substitution reaction, but in some cases it may undergo nucleophilic substitution reaction also. In aryl halide, why the chance is less? Because due to resonance of CCl bond, this has partial double bond character, the bond is quite strong and replacement cannot take place readily. Just I am writing it. In aryl halide, due to resonance, CCl bond has partial double bond character. As a result, bond is quite strong and less readily substitution reaction takes place. Okay, let us up to this for today's class. Next day I will go in detail about nucleophilic substitution reaction detail. Thank you all of you. Hope for next class.